The normal distribution is so important for a whole set of Six Sigma statistics. In fact, Six Sigma is a term that is directly linked to the normal distribution, that we have to talk about it. Hello, I'm Tom. Welcome to my channel where we talk about continuous improvement in an industrial setting. And today it's going to be a bit of a statistics video, not really core to continuous improvement, but the thing is that this normal distribution, it is in so many of the tools that we use, especially in Six Sigma, but also in all kinds of things like what is a reorder point and how do you have your stock levels with the safety stocks and stuff like that, that you use it a lot. So I think it is important that you know what it is. If you have perfect knowledge of the normal distribution, click away to some cat video, but this might be good for you and hopefully also something to maybe share with colleagues to explain the normal distribution a bit to them, because we use it almost everywhere. Now, if we check, the distribution, it's a part of statistics, it's part of probabilities. So let's get ourselves a random number generator. We have this here, little die with 1 to 6 on it, and if we throw one of those dice, then we can get basically any of these results with equal chance, right? If you throw it 6 times, you sort of expect it to be a 1, a 2, a 3, a 4, a 6. You will see that, if you do that, you'll get 2 2s and no 1, because, randomness happens. But if you throw it 1,000 times, or maybe 6,000 times, you would expect about 1,000 1s and about 1,000 2s and sort of like that. That type of distribution is called a uniform distribution. Every option has a uniform or the same chance of happening. And that is how we draw it. You have the 1 to 6 and they all have the same level of happening, the same probability or the same distribution when you have loads of them, right? Now, that is when you have one of those, D6 is one of those 6-sided dice. What if we take 2 of them, right? And you know this as well, there's plenty of games that revolve around it. The minimum, of course, when you throw 2 6-sided dice is 2. The maximum is 12. But you also know that there's only one chance to throw a 2, not one combination, 2 1s, and there's 6 combinations that can make a 7. Each of the numbers on the first die has a companion number on the second die that make it a 7. So there's a lot of chance to make a 7, and then a 12 again, you have to have 2 6s, so the chance is pretty low. And what we'll see here is a pyramid shape. So this is not really the nice bell curve yet, but you do see it is a bit different. Now, what happens if we take a whole bunch of those dice? So let's say we take 10 6-sided dice. If they all land on a 1, all 10 of them, we get a 10. If they all land on a 6, we get 60. The chance of getting to 35 is a lot higher because there are many variations of how the dice fall that can make 35. Now, what happens with that one is that it will look like this nice bell curve. And this is a normal distribution. Now, I should say this looks like, this tends to be a normal distribution, approaches normality. The more dice you add, the closer you get to true normal. And, well, for all practical intents and purposes, around 8 or so dice, you are so close to a normal distribution that we would generally say normal. That number 8 is also, it's one of them things that comes back a number of times in rules of thumb on how many samples should there be in a subgroup before you use standard deviation versus range methods. And so that's all sort of based on that same concept that if you have 7 to 8 degrees of freedom, basically when you throw 8 dice, that's roughly when you get to a very nice normal distribution. Some, of course, distributions will be there a bit sooner, some will be there a bit later. That's a good rule of thumb. Now, for the more nerdy inclined, you know that the 6-sided die is not the only one, right? You also have a 10-sided or only 4-sided or favorite 20-sided. If you throw a whole hand of these role-playing dice, basically of these different sided dice, you get the same. The numbers will be different, but you get the same normal distribution. And that is a very important sort of fact of probability. The more different sources of variation you add, the closer things get to true normal distribution. Now, where do you see this normal distribution? You see it almost everywhere, and that is the fun fact about it. So, when we look, for instance, at the height of males and females, and these are world statistics from a couple of years ago or so, but the idea is that when you just measure a whole set, a nice and big set of humans, what you will see is that women tend to be, on average, 1 meter 63 centimeters tall, which is 5'4" for my American friends, and males, men, get to 176. So there is a difference in the average. On average, if we just take a whole lot of people, men tend to be a bit taller. Now, you also see that there is this distribution, right? So we got a normal distribution, just a bit longer, but the shape is the same as that one. And that means, and you notice, some men are a bit taller, some men are a bit shorter than 176. In fact, there are some short men who are definitely shorter than tall ladies. So there's this overlap where it can be, both men and women sort of can have the same heights. So are they really different? Well, if you take enough samples, as this study did, you can say, yeah, well, this holds true if you measure tens of thousands of people. There is still a difference in their average height of 13 centimeters or 5 inches. So that is quite a significant difference. Significant. That is one of them statistical terms as well. The significance, that is decided by how big are these overlaps, how far are they apart, how many samples do we have that we still see it, and can we say with a certain certainty that the averages of these two sample groups, or in this case, real populations, is different. So is it just a sort of a fluke, or can we say that men really tend to be taller than women? Now, in this case, we can. Even though there is quite a bit of overlap, we have measured so many people, and we still get that difference in height that we will say, yes, there is a statistically significant difference. What does it give us? Nothing and quite a lot at the same time. But this concept, it applies to a lot of the stuff we use, especially in Six Sigma statistics as well. Now, one other thing here. So we have men who are roughly, there is a standard deviation of 7 centimeters here. So that means that most men are between, well, about 160 and 190. I'm 196, so I lie outside of this here population. That's because us Dutch people tend to be a bit taller. This same number, if you take only men in the Netherlands, would be 181 or 183, depends a bit on which years and data sets you take. So we are taller. Is that significantly different? Yes, it is, but that's not the point of this video. What if somebody does not have legs? Right? We have people who got into an accident or have a birth defect or things like that, and they simply don't have legs. They're going to be, what, 1 meter? Maybe 120? They're going to be somewhere here. That's completely not in the normal distribution. The same goes for people with dwarf growth. It is a condition that causes them to be a lot shorter. Sort of the same, but not as dramatically, will also happen when there was a famine. and a whole age group that was in their growth years during the famine will not have grown as tall. They will be usually still somewhere in the distribution, but really to the left side. So these things, they are not normal causes of variation. The normal distribution will show you normal causes of variation, or in terms of SPC and related Six Sigma statistics, common cause variation. Now the no lags, the dwarf growth, the big famine, those things, they're all special causes of variation. That is an interesting concept to remember for what we're doing in our factories as well. So before we get to the applications in the factory, the one nice thing when we see that it is normally distributed is that we know a lot about this normal distribution. We can make a bunch of assumptions. For instance, we know that most people will be quite close to the mean, right? And you may have seen these pictures also. So what they then show is that you have a mean, and if you make equal lines left and right, and here is the standard deviation, or sigma, that between the plus and minus 1 sigma, so this here area, we have 68% of all of the values. And that percentage increases the further we go out. So if we go to plus or minus 2 standard deviations, you get to about 95. Or if you get to plus 3 minus 3 standard deviations, you get to that 99.7%. That is one you will see a lot in SPC and slightly also in other Six Sigma statistics. This, by the way, is not 6 sigma, even though plus and minus 3 would be 6 together. No, real Six Sigma says plus 6 minus 6. But you will know, for instance, CPK. And there we do put 3 sigmas to 1. So you hear a lot of sigma already. And if you follow this channel, if you are in continuous improvement, you know the Six Sigma rules. And you know a couple of the tools that we use for that use this sort of probability stuff, right? So we got a couple of them, like SPC, Statistical Process Control. Now, process control is check whether or not a process is behaving as it should. Right, so we take a couple of samples, and we know that a process should be centered at 176. We take a sample, it's 180. We say, that is a bit high. Maybe we should correct something. So we need to get down to our target. That is basically what process control does. Now, statistical process control will say, okay, 176, the sigma level is 7. So there is about 86% of stuff is happening between plus and minus 7. So between 169 and 183. So 180, but there's actually quite a good chance of having a sort of a random, in this case, man, but a random product coming off our line with 180 when we have the same type of distribution. So we shouldn't worry. That is the statistical part of process control, and that uses the idea that your process has a lot of variables. So if the process has really only one variable, you would have a uniform distribution, you cannot use SPC. If there are 2 variables, we'll already get a bit closer, 3, 4, but we know that in our process we have plenty variables, and we're not talking about those 2 settings that you actively manage. There is a bit of heat, a bit of vibration, there is some variation in the product itself, there is all kinds of things, like that little bit of residue the previous product left, and then it gets picked up and then it doesn't. Your processes, they all have their own physics, but they all have loads and loads of sources of variation. And as long as those are common cause variations, so they sort of happen the whole day to every product, then they will cause a normal distribution to happen in the output products. So statistical process control will take that assumption and say, well, since we know it's normally distributed and since we know that there are percentages here, we're basically going to say, let's look at the previous one, and if we have a product that should be 167 long and it has a standard deviation of 7, so if we do 3 standard deviations, we get 197. That is 99.7% of our products will fall in that. So if you hit a 196 or 197 once every day or a couple of days, that's sort of normal, right? If you make about, well, it's a bit more than 100, if you make about 300 products, you would expect one of them to come up at 196, 197, right? So when we see it, we can ignore it. If we have a 200 one, we'll need something like a couple thousand products before we expect it. That is strange. So we use the statistics to say this is still normal, this is strange. And when it is strange, we assume that there was a special cause of variation, and those we want to attack when it is in our processes. We assume that the whole thing has shifted, that we're actually looking at a different population of products, right? We're looking at women instead of at men. Of course, in the real life, we would probably do that with different characteristics of those products. But in your production process, maybe one of the levers has just shifted. And because of that, all of the products are now slightly bigger. Just a bit. It just shifted a bit. Many of them will still fall in that range that we sort of see as normal, but a couple of them will really fall outside. That is where you use the statistical predictions. It goes wrong. Also, when you see a whole bunch of them that are here, right? So we expect a couple of them to be a bit bigger, a couple of them to be quite a bit smaller, and most of them to land in the middle. So if we have 5 or so that are here, one after, that's also strange. So statistically, we can say, no, go and investigate the process. That is statistical process. It's all based on that normal distribution. We can also use it to compare things, so like we did here with men and women, and we say, are they significantly different? You can do the same things when you have, for instance, Gage R&R, right? Repeatability, reproducibility, where you say, we're going to measure what should be the same products, and we'll have 2 operators measure them. They get different results, right? So they have slightly different curves. If those curves overlap mostly, we'll say, luck of the draw. One of them just sort of read the meters slightly differently by chance, or maybe even the products themselves were slightly different. This is within normal expectations. If they're a bit further apart, we'll say, no, those operators have a different way of sampling testing. So the measurement system is different for one operator than for another. We should do something about it. So you see, again, these are very practical comparisons. We can also compare a new product variation to the current product that we have, use statistics to sort of check, do we expect, and then often we use a binomial distribution, but we use this idea of we know what type of distribution we have, and we know which percentages are there, and we can sort of say, now we're pretty confident that this is different, or not. But that only works if we understand, or actually if we follow that assumption that there is a normal distribution. And then one of the most literal ones, the process capability. It's really a part of 6 sigma. As I said, sigma is standard deviation. That is the same. A sigma and a standard deviation, they are the same. And a CPK, a process capability index coefficient, it looks at how many standard deviations are there between the center and some specification that I have. If it is exactly 3, the CPK will come up 1. It'll say your process is barely capable, 1 in capability. That means that 99.7% of your products will be within specification. So that's sort of shorthand for 100%. Now, in statistics, you never get to 100%, but this is sort of accepted as 100. A CPK of 2, that's 2 times 3 standard deviations, 6 standard deviations, gives you so much room that your process can wiggle a little bit and you still have time to react before you really go over your specifications, over your tolerances. But all of them, they all assume this normal distribution. And when you do a t-test or a z-test or ANOVA and things like that, they all assume normality, which is a good assumption. Right? Most of your processes, most of your products will have so many variables that it comes down to pretty close to normal. But do test this, because if you have in the products that you test, let's say we've got a nice bakery and or making pancakes, I like baking. The first pancake you make, when the pan is not really hot yet, they always go wrong. Right? That is not a normal cause of variation, not common cause variation. So if you include them in the whole population, what you will see is you will see a spike and the rest of the bell curve. That little spike is actually just another distribution hidden in there. You need to take them out, because if you leave them in, you don't really have a normal distribution. Those are the things that you sort of need to check. So make a histogram, just plot the values that you have, and then how often do all of those values show up in your data. If it looks like this, don't use SPC on it. If it looks like this, yeah, you can. There are tests for normality. I think that most applications we have within the continuous improvement world don't really need them, but you could do a QQ graph, check it, or you could do a test for normality just to be sure. Most of the statistical packages have them built in, but an easy way, just make your histogram and check visually, because it will also allow you to immediately see, where is a strange spike that might require your attention. So that's that normal distribution. Again, this happens everywhere. This is natural variation, normal distribution, a standard type of deviation. It happens when you have variables, many variables, and you have that everywhere in nature, but also in your production processes. And that is why, by understanding that concept of we have some of those variations, most of the tools in Six Sigma, they are ways of checking, is one sample, is it part of the larger population, or is it from the same population as another sample? And we use statistics to calculate the probability that you would get these samples when you know that the population is there. Is that chance at least more than about 5% for most sort of comparison statistics, or is that chance more than 0.3% for SPC? So SPC knows we'll have another shot at it, and we'll break that barrier quick enough. So is there a certain chance that you would get this when the process is still centered, the process is still doing what it was always doing? Then we accept it as good. But if it falls outside of those distributions, SPC will trigger and say, check your process. A t-test will say there is a significant difference, so probably these two products are not the same, or these two operators don't measure in the same way. CPK doesn't really use that concept of checking differences, but this will say, if you have a CPK of 1 or better, higher than 1, then the chance of getting faulty products is basically 0. So we can accept it. And you can calculate CPK not by checking all the products that you make, but by sampling part of that population. Just take 10 products out, you check them, based on those 10, you calculate the mean and the standard deviation, and then you say, oh, okay, but now we take 3 of them standard deviations, and that's the lowest and the highest that the whole batch will have had. So you extrapolate. Those are the type of statistics that we use. That is what people in your quality department, in your continuous improvement department, should really understand as a concept. Now, if you have more questions on that normal distribution or how you get there or how it works, please do, write in the comments. And these are a couple of the concepts that are not easy to grasp, not natural to grasp. There are very few people who have a natural understanding of statistics, but many people who work with them. So, let's share the questions. Other people, please also do answer questions, but do not be afraid to comment on this. It's an important part of your continuous improvement, especially Six Sigma learning journey. So, hope you liked that slightly different video in my series. If you did, don't forget to hit that like button. And also, I get a lot of statistics from YouTube, and I see that about 90% of you watching are not subscribed. So, what's that? I make a nice video every week. If you subscribe, hit that bell icon. You get some notifications about that. It also helps a little bit with the algorithm. So if you like more of my videos, subscribe as well. For now, I wish you the best of luck understanding statistics. And as always, don't forget to also enjoy the continuous improvement journey.